going to discuss about graph theory or network topology. Network topology is the study of properties of the network. So we are going to study the properties of the network. So network topology is the study of properties of the network which are unaffected when we stretch or twist or distort the size and shape of the network. Okay. So properties, actually network topology is the study of properties of the network. We are going to study the properties of the network. These properties cannot be changed even if you stretch the network or distort the size and shape of the network or twist the network. Okay, so when stretch or twist or distort the size, if we stretch, twist or distort the size and shape of the network, the properties of the network cannot be changed. So network topology is the study of properties of the network. Graph theory. Let me draw the graph for a given network. Okay, so first let us take one network. So let me consider this network. So V1, R1, R2, I1, R3, R4, R5. When all the elements, okay, if you want to take inductor, you can take one inductor. You can take capacitor also. When all the elements, resistors, inductors, capacitors in a network are replaced by lines with circles or dots at both ends. Okay. So when all the elements means resistors, inductors, capacitors in a network are replaced by lines with circles or dots at both ends, the configuration is called a graph of the network. The configuration is then called graph of the network. Okay, so let me replace all elements with lines. Okay, so here the graph of network is drawn. The graph of network is drawn by keeping all points of intersection of two or more branches and representing the network elements by lines. Representing the network elements by lines. Voltage and current sources are replaced by their internal impedances. So resistors, inductors, capacitors are replaced by network elements are replaced by lines, and voltage source and current source. These two sources are replaced by their internal impedances. Okay, you know, right? What is the internal impedance of ideal voltage source? It is 0. What is the internal impedance of ideal current source? It is infinite. Okay. Hence, it is to be replaced by an open circuit, replaced by short circuit. So, voltage source should be replaced by short circuit because it should be replaced by its internal impedance. Internal impedance of an ideal voltage source is 0. Okay, so voltage source is replaced by short circuit, and current source is ideal current source is replaced by open circuit, because an internal impedance of ideal voltage source is, ideal current source is infinite. Okay, internal impedance of an ideal current source is infinite means that should be replaced by open circuit. Okay, so in order to draw a graph of the network, of the given network, all elements means resistors, inductors and capacitors are replaced by lines. Voltage source is replaced by short circuit, current source is replaced by open circuit. Okay, so let me draw the graph of the given network. Okay, so R1 is represented by line, V1 is replaced by short circuit, R2 is represented by line, current source is replaced by open circuit, R3 is replaced by line, R4 is replaced by line, R5 is replaced by line, inductor is replaced by line, capacitor is replaced by line. Okay, this is common point. Okay, so you can have the graph like this. We don't have the graph like this. This is the graph of the given network. Okay, this is the common point. This reference element R1. R1 is replaced by this line. R2 is replaced by this line. R3 is replaced by this line. R4 is replaced by this line. R5 is replaced by this line. L is replaced by this line. C is replaced by this line. Okay, so this is the graph, the given network. This is not oriented graph or directed graph, as it is having no directions. Okay, so next coming to directed or oriented graph. Okay, so let me take that previous network. Okay, so let me give directions. Okay, this is I1. Okay, this is I2. This is I3. This is I4. This is I5 is the current which is going to this. Okay, so now you take that graph of the given network. Okay, this is the graph of the given network, right? Then here give directions. Then this is called oriented graph. Oriented graph. Oriented graph or directed graph. Okay, this is not an oriented graph. This is simply graph. Okay, so this is an oriented graph. A graph with directions or orientations represented for each branch is known as directed graph or oriented graph. Coming to subgraph. Okay, let us take one graph. This is the graph. Let us take an oriented graph. All are nodes of a graph. Nodes of the graph. Okay, how many nodes do we have? 1, 2, 3, 4 nodes. How many branches do we have? 1, 2, 3, 4, 5, 6 branches. Okay, so let me draw subgraph. Okay. This will be graph, subgraph. Okay, so here see a graph. This is GS. This is G. So this is main graph. This is subgraph. A graph GS is said to be subgraph of a graph G. It is the subgraph of. It is GS is subgraph of graph G. If every node of GS is a node of G. Okay, so this is node of GS is node of G. All nodes of every node of GS is a node of G. Is a node of G. Every branch of GS, every branch. Okay, this is a branch of GS. This is a branch of GS. All are branches of GS. Okay, every branch of GS is also a branch of G. Okay, branch 2, branch 3, branch 1, branch 4. All are branches of, these are all branches of GS. Okay, every branch of GS is also a branch of G. Then this is called subgraph of the given graph. So this is the subgraph of the given graph. Okay, every node of GS is a node of G. Every branch of GS is a branch of G. That's why it is a subgraph of the given graph. Okay, let me take one graph, oriented graph or directed graph. Node. It is a point of intersection of two or more branches. Okay, this is branch. Okay, this is also branch. This is also branch. This is also branch. This is also branch. Okay, interconnection of two or more branches is called a node. Okay, this is node. Node 1. This is also a node. Node 2. This is also a node. Okay, node 3. Intersection of two or more branches is called a node. Okay, intersection of two or more branches is called a node. This is also a node. Okay. Coming to branch, a line joins one network element or a combination of elements between 2 points. Okay, it is a line which joins a network element, or it is a branch. Branch means it is a line. It is a line connected between a line which is representing the given network element. Okay, a line which is representing the given element, and that line is connected between any two nodes is called a branch. Coming to degree of a node. Okay. Degree of a node is, it is the number of branches connected to a node. What is the degree of node 1? 1, 2. Number of branches connected to the node 1 is 2. What is the degree of node 2? Number of branches connected to node 2 is 3. 3 branches are connected to node 2. That's why degree of a node of, degree of a node 2. Degree of a node is the number of branches connected to a node. Degree of node 2 is 3. What is the degree of node 1? 2. What is the degree of node 3? 2, because 2 branches are connected to node 3. What is the degree of node 4? 3, because 3 branches are connected to node 4. 3. A tree is a part of oriented graph. So first let me take one oriented graph so it is easy to draw. A graph without directions is called here a graph with directions is called an oriented graph or directed graph. Branches, let me mention branches. A, B, C, D, E, F. Nodes. Node 1, node 2, node 3, node 4. 4 nodes. How many branches? 1, 2, 1, 2, 3, 4, 5, 6, 6 branches. Okay. So a tree is a part of directed graph containing all nodes of a graph. Containing all nodes of a graph without any closed path. Okay, so let me draw a tree. Okay. A tree is a part of oriented graph containing all nodes of a graph. Let us draw a tree. A tree should contain all nodes of a graph. Okay, this is a given graph. This is a given graph. Okay, a tree should contain all nodes of a graph. How many nodes do we have? 4 nodes, right? So that a tree should contain all nodes of a graph. Okay. It should not contain any closed paths. Without any closed paths. Okay, so without any closed path, let me draw a tree. This is one of the trees. It is a tree because it contains all nodes of a graph. It is a tree. It is a tree. It contains all nodes of a graph. Okay, so node 1, node 2, node 3, and node 4. It contains all nodes of a graph without any closed path. And without any closed path. It is having no closed path, right? It is having no closed paths. Okay, so it is a tree. Okay, let me draw one more tree. It should contain all nodes of a graph. So it should contain all nodes of a graph. This is a tree. This is also a tree. This is also a tree. It is containing all nodes of a graph. Okay, this is also a tree for the given graph. This is the given graph. This is also one of the possible trees. You can have one more tree. So this is also a possible tree. This is also a possible tree. Okay. It is containing all nodes of a graph. All nodes of a graph having no closed path. Okay. So coming to the properties of tree, it consists of all nodes of a graph. Consists of all nodes of graph. Okay. So a tree should contain all nodes of graph. Next here, see. For an n node graph, a tree has n minus 1 branches. Okay, how many nodes do we have here? N is equal to 4. For an n node graph, the branches of the tree will be n minus 1. Okay, let me check. Okay, here, how many nodes do we have in the given graph? 4 nodes. Okay, a tree should have n minus 1 branches, right? So, number of branches of tree is equal to n minus 1. So, let me check. N minus 1 is equal to 4 minus 1. 3. We got 3 branches only, right? 3 branches. 3 branches only. 3 branches only. Again, here also 3 branches. 3 branches. Again, here also 3 branches. Likewise, you can draw all possible trees. Likewise, you can draw all possible trees for the given graph. Okay. And coming to the next property, there cannot be any closed path in a tree. Okay. Next, number of possible trees is equal to set of Reduced instance matrix. This is AR. AR. Okay. Det of AR into AR transpose. AR transpose. I'll come back to this. AR. Reduced instance matrix. Okay. Det of AR into AR transpose. Use the number of possible trees for the given graph. Next, pick. The branch of a tree is known as a twig. Okay, see, all are twigs. All are twigs. Okay, the branch of a tree is called a twig. Okay, how many twigs do you have here? 3 twigs. Okay, so this is the tree for the given graph, right? Okay, so all are twigs. All are twigs. Okay, how many twigs we have here? N minus 20 twigs. Okay, 3 twigs. 3 twigs. Twigs. The branch of a tree is known as twig. A twig is represented by a thick line. Thick line. It is represented by thick line only. Okay, thick line. Simply it is all are twigs. This is a tree. All are twigs. 3 twigs. Represented by thick line. Represented by a thick line. Coming to co-tree. Co-tree means what is the given graph? This is the given graph. This is the given graph, right? This is the given graph. Okay, this is what? This is tree. Two trees. I've drawn 2 trees, right? Okay, this is the given graph, right? Okay, so coming to co-tree. Co-tree is the part of oriented graph. It is a part of oriented graph. It is a part of this graph only, this directed graph or oriented graph. That is not covered by the tree. It is known as co-tree. It is a part of graph. The part which is not covered by a tree is called a co-tree. Means here, see, if you take this as a tree, this is a tree, right? You take this as a tree, then co-tree would be like this. It is a part of oriented graph which is not covered by a tree. Means which part is not covered by a tree? This part is not covered by a tree, right? This part is not covered by a tree. Okay, this part is not covered by a tree. So this is called co-tree. It's called co-tree. Okay, let me take one more tree. This is a tree, right? It is containing all nodes of a graph and having no closed paths. So this is also a tree. For this tree, if this is the tree for a given graph, then how can I draw a co-tree? Co-tree is the part of oriented graph which is not covered by a tree. Okay, which part is not covered? This is not covered. This branch is also not covered. This branch is also not covered. Okay, so this is co-tree. This is called co-tree. Okay, can give directions. This is called co-tree. Co-tree means the part of a directed graph that is not covered by a tree. That is not covered by the tree is known as co-tree. A co-tree is represented by dotted configuration. Okay, dotted configuration. Okay, dotted configuration. Link or chord. The branch of a co-tree is known as a link or chord. and is represented by dotted line. So branches of core tree are represented by dotted line, right? Branches of core tree are represented by dotted line. Okay, dotted line, dotted line, dotted line, dotted line, dotted line, dotted line. Okay, dotted line. So you take another tree. This is also one of the possible trees. One of the possible trees, right? It is containing all nodes of a graph and having no closed path. For this tree, what will be the core tree? Core tree will be like this. Okay, this is the core tree in new direction. Core tree represented by a dotted configuration. Represented by core tree is represented by dotted configuration. Okay, links or chords. The branch of a tree, sorry, the branch of a core tree is called link or chord. Okay, this is called link, chord, or link or chord. Link. How many links do we have here? 3 links. Okay, and is represented by dotted lines. Number of branches in a directed graph is equal to number of figs plus number of links. Okay, branches of tree, branches of core tree. Okay, so number of branches of a graph, number of branches of a graph is equal to, okay, branches of a tree n minus 1 plus number of links, branches of core tree. This is what? Branches of tree, branches of tree, branches of core tree, branches of core tree. Okay. Already you know, right? Number of branches of tree is given as n minus 1. Let L is the links, number of links, nothing but number of branches of core tree. Number of branches of core tree. Okay, number of branches of tree is equal to n minus 1. Number of branches of core tree is equal to L. Okay, so let B is the number of branches of the given graph, which is equal to n minus 1 plus L. Then what will be the number of links? L is equal to B minus n plus 1. Okay. Let B is the number of branches of a graph. Okay, so you can find the number of links. Here, see how many branches do we have for the given graph? Number of branches B is equal to, or n is equal to 1, 2, 3, 4, 5, 6 branches. Number of branches of tree is equal to n minus 1 or B minus 1, which is equal to 4 minus 1, 3. Okay, then you can find the number of branches of core tree L. So L is equal to B minus here b minus n minus 1, which is equal to 6 minus here, sorry, here b is equal to 6, right? N is equal to number of nodes. Here n is not equal to b. Okay, here n is equal to number of nodes. N is equal to number of nodes. Okay, so here n minus 1 is the number of branches of tree. Branches of tree means n minus 1. How many nodes do we have for the given graph? 1, 2, 3, 4. 4 nodes. That's why 4 minus 1. Okay, 4 nodes. Number of nodes is equal to 4. 4 minus 1 is equal to 3. Okay, so number of branches of tree is equal to 3. Okay, so so 6 minus, how many nodes do we have? 4 plus 1, which is equal to 3. So here see, how many branches do we have in co-tree? 1, 2, 3. 3 branches. Okay, likewise we can find the number of links. Number of links or number of chords. Number of links are nothing but number of branches of a co-tree. Okay, let b is the total number of branches of the given graph. Let b is the total number of branches of the given network, given graph. Okay, then then total number of branches of a given graph is equal to number of branches of a tree plus number of branches of co-tree. Number of branches of tree plus number of branches of co-tree. Right? So what is the number of branches of tree? N minus 1. What is the number of branches of co-tree? L. So you can find L. L is equal to b minus n plus 1. B is the number of branches of graph. Number of branches of the graph. So 6. Okay, n is the number of nodes of the graph. 4. So plus 1, which is equal to 3. 3 is the number of links. Okay, now coming to incidence matrix. Incidence matrix. A matrix representing the relation between number of branches representing the relation between number of branches and number of nodes. Number of nodes. Okay, so for this oriented graph, let me indicate branches A, B, C, D, E, F. All are branches of the graph, right? Okay, so branches A, B, C, D, E, F. How many nodes do we have? 4 nodes. 1, 2, 3, 4 nodes. Okay, so 1, 2, 3, 4. Okay, so it is what? Number of branches. It is what? Number of nodes. So a matrix representing the relationship between number of branches and number of nodes in a directed graph is known as incidence matrix. It is known as incidence matrix. The matrix representing the relation between number of branches and number of nodes in a direction graph is known as instance matrix. Okay, so here, after forming this matrix, coming to properties, determinant of instance matrix of a closed loop is 0. So this is indicated by AI. 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 Okay, this is indicated by AI. Instance matrix. Okay. So it is a matrix depending on the relation between number of branches and number of nodes. So after forming instance matrix, here properties determinant of data of this is coming to properties. Set of AI is equal to 0. Data is equal to 0, and algebraic sum of the column entries of an instance matrix is 0. Algebraic sum of the column entries of an instance matrix is 0. Okay. I'll come back to this. Coming to reduced instance matrix, the matrix obtained by deleting a row of the instance matrix is known as reduced matrix, reduced instance matrix. Okay, so here means you're going to get how many columns we are going to get? 1, 2, 3, 4, 5, 6. 2, 3, 4, 5. Okay. Yeah. 1, 2, 3, 4, 5, 6. 6 columns. 6 columns. 4 rows. 1, 2, 3, 4 rows. Okay. This is instance matrix set. So by deleting a row of the instance matrix is known as reduced instance matrix. Normally we delete this row corresponding to reference node. Okay, 4 is reference node, right? Okay, we delete this row. Okay. Formation of an instance matrix. Okay, AI. 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 Instance matrix. Okay. Obtain directed graph for the given network. Okay, procedure for forming an instance matrix. Obtain directed graph for the given graph, for the given network. Next step. Assign +1 in the matrix if the row, sorry, if the arrow of a branch is oriented away from the node. Assign -1 in the matrix if the arrow of a branch is oriented towards the node. Assign 0 in the matrix if the branch is not connected to a node. So for the given network, see, if this is the given network, okay, this element is replaced by short circuit, okay, replaced by line, replaced by line, replaced by line, replaced by line. Okay, so you're going to have graph for the given network will be like this. If directions are not given, you take your own directions. Okay, so this is what? This is oriented or directed graph. Okay, what is step? First step to form instance matrix. Okay, obtain directed graph for the given network. So this is the given network. Okay, you obtain directed graph. Okay, you represent all elements are replaced by lines. Okay, so first you obtain oriented graph for the given network. Okay, then after you have to form instance matrix like this. Assign +1 in the instance matrix in the matrix if the arrow of a branch is oriented away from the node. Assign -1 in the matrix if the arrow of a branch is oriented towards a node. Assign 0 in the matrix if the branch is not connected to a node. Okay, so let me have instance matrix. It is a matrix representing the relation between number of branches and number of nodes. So A, B, sorry. Let me have instance matrix. Branches A, B, C, A, B, C, D, E, F. So 6 branches. How many nodes do you have? 1, 2, 3, 4. 4 nodes, right? Okay, so it is the matrix depending relation between number of branches and number of nodes, right? Okay, so yeah, here see. Assign plus 1 in the matrix. Assign plus 1 in the matrix if the arrow of a branch is oriented away from the node. So see here, see. From this graph, see. Node 1. This is node 1. Node 1. Okay. Assign plus 1 in the matrix if the arrow of a branch is oriented away from the node. Okay, so branch A is oriented or directed away from this node, right? If it is oriented away from the node means you write plus 1, assign plus 1. Next coming to branch 2. Okay. Branch B. Branch B is not connected to node 1, 0. Branch C is connected. It's connected and oriented away from the node. So you assign plus 1. Coming to branch D. Branch D is not connected. Assign 0. Assign 0. As branches E and F are not connected to node 1. Okay, now coming to this node 2. Okay. Branch D is connected and which is oriented. See, branch D is connected. Okay, and which is oriented away from node 2. Away from node 2. Away from node 2 means assign plus 1. Assign plus 1. Next, branch A is also connected, but it is oriented towards the node. Means assign minus 1. Branch B is also connected to node 2 and which is oriented away from node 2. Means assign plus 1. Other branches are not connected. So assign 0, 0, 0. Other branches are not connected. Node 2, 2. Coming to node 3. Node 3. This is node 3. Branch B is connected, branch E is connected. Branch B is okay. Arrow of this branch is oriented towards the node. If it is oriented towards the node means assign minus 1. Branch of E. Sorry, branch E. Arrow of this branch is directed away from node 3. Away from node 3 means branch of which branch? Branch E. Branch E is directed away from node 3. Assign plus 1. Other branches are not connected to node 3. You assign 0. Next, come to node 4. Branch C, D, E. These 3 branches are connected to node 4. Branch C, D, E. These 3 branches are connected to node 4. Okay. And arrows of these branches are oriented or directed towards the node. Okay. If the arrow of the branches directed towards the node means assign minus 1. So assign minus 1. Sorry, CDE, right? Okay, assign minus 1, assign minus 1, assign minus 1. Okay. Other branches are assigned to node 4, so assign 0, 0, 0. Okay. This is an instance matrix AI. Okay. Instance matrix. So here, properties. What are the properties of the instance matrix? Determinant of instance matrix of a closed loop is equal to 0. So you can find data of this. If you find data of this instance matrix, then it is equal to 0. The data of this is 0. Coming to the next property, algebraic sum of column entries of an instant matrix is 0. What are the column entries? How many columns do we have? Column 1, column 2, okay, column 1, column 2, column 3, column 4, column 5, column 6. Okay, see, add all entries, column entries of this column. Plus 1 minus 1, 0. Okay, coming to this column. Plus 1 minus 1, 0. Coming to this column. Plus 1 minus 1, 0. 0. Coming to this column. Plus 1 minus 1, 0. Plus 1 minus 1, 0. All 0. 0. Okay, so you can form instance matrix like this. Reduced instance matrix. What is reduced instance matrix? A reduced instance matrix is obtained by deleting a row. Okay, normally we delete delete a row. We delete a row which is corresponding to reference node. Okay, so anyhow, this is the instance matrix. We delete this row. Okay, we delete this row. Okay, corresponding to node 4. Then we will get this. You take the instance matrix is equal to 3, 4. Okay, to delete this row. To delete this row. Then you are going to get reduced instance matrix. So you're going to have reduced instance matrix like this. Okay. By deleting last row, by deleting this row, you can form reduced instance matrix. Okay, so you can find number of possible trees. Okay, this is a given graph, right? Okay, this is the graph. This is a given graph. Okay, so you can find the number of possible trees. Number of possible trees is equal to depth of, right? Depth of AR into AR transpose AR transpose. Okay, then you can get number of possibilities. Okay, 8. You can also draw all possibilities. See, this is the given graphic. You can draw all possibilities. This is one of the possibilities. Okay. This is one of the possibilities. Next, this is one of the possibilities. This is also one of the possibilities. A tree should contain all nodes of a graph. It is containing all nodes of a graph, having no closed paths. Having no closed path. Okay. Having no closed path. All are okay. 1, 2, 3, 4. Likewise, you'll get four more trees. Okay. You can also have tree like this. This is also a tree. One, 2, 3, 4, 5. You can also have tree like this. This is also a tree. See, containing all nodes. 4 nodes of a graph. You can also have tree like this. Containing all nodes of a graph. Okay, 6, 7. Okay, you will get one more. Check it out. draw the oriented graph of network shown. Write the instance matrix. Okay, this is the given network. Okay, see, this is voltage source is replaced by short circuit. Okay, first let me have network with current direction. Okay, it is having no currents, right? Okay, so assume different branch currents in the given network and different nodes like this. Okay, now you can draw an oriented graph like this. Okay, see here. This branch is, okay, this R1 is represented by line. R1 is represented by line. V1 is replaced by short circuit. R2 is replaced by short line, and V2 is replaced by short circuit. C1 is replaced by line. Okay, inductor is replaced by line. Current source is replaced by open circuit. L2 is replaced by line. C2 is replaced by line. R3 is replaced by line. I2 is replaced by open circuit. Okay, so you get graph. Okay, if follow these current direction, so you can get oriented graph like this based on the directions of current. So based on the directions of current, we can have oriented graph. Oriented graph. Right. Okay, for this oriented graph, let me have instance matrix. A is equal to, so how many branches? 1, 2, 3, 4, 5, 6, 7 branches. Okay, 1. A, B, C, D or nodes. Okay, branches. Here this is branch 1, branch 2, branch 3. This is branch 2. This is branch 5. This is branch 6. Branch 1. Branch 1, branch 2, branch 3, branch 4, branch 5, 7. This is branch 1, branch 1, branch 3, branch 5, branch 7. Okay. So here see, it represents the relationship between number of branches and number of nodes, right? Okay, so how many branches do we have here? 7 branches. How many nodes do we have here? 5 nodes. Okay, so with respect to node A, okay, branch 1 is connected as well as branch 2 is connected. Both branches are connected to node A. Okay, branch 1 is connected. Okay, node A, branch 1 is connected, branch 2 is connected. The arrow of branch 2 is oriented away from node A. The arrow of branch 2 is oriented away from node A, means assigned +1. So +1 is assigned. The arrow of branch 1 is oriented towards node A, means assigned -1. Remaining branches are not connected to node A, that's why assigned zeros. branch B, node B. Here node B. Branch 2, branch 3, branch 4. 3 branches are connected to node B. Okay, so 2, 3, 4 are connected. Arrow of branch 2 is oriented towards node B. That's why assign -1. Arrow of branch 3 is oriented away from node B. That's why assign +1. Arrow of node 4 is arrow of branch 4 is assigned. Sorry, arrow of branch 4 is oriented away from node B. Assign +1. Coming to this node. Node C. Okay, branch 4, branch 6, branch 5. These 3 branches are connected to node C. Okay, so branch arrow of branch 4 is oriented towards node C. That's why I said -1. Arrow of branch 5 is oriented away from node C. Assign +1. Arrow of branch 6 is oriented away from node C. Assign +1. Likewise, you can form instance matrix. Trisect matrix. Matrix representing the relation between number of link currents and number of branch currents in a direction graph is known as trisect matrix. The trisect matrix formation. Select a tree and co-tree from the directed graph. Determine the number of links. The number of trisect currents to be assigned equals the number of links. Okay, assign trisect currents such that they flow through only one link in the path. Direction of trisect current is the same as the direction of link. Assign +1 in the matrix if the directions of trisect current and branch is same. Assign -1 in the matrix if the directions of trisect current and branch are opposite. Assign 0 in the matrix if the trisect current doesn't flow through that. Let me form trisect matrix. So this is the given network. This is the given network. So you can have directed graph like this. You can have directed graph. Right? Okay, all elements are replaced by lines. Here, see, yeah, all elements are replaced by lines. This voltage source is replaced by short circuit. Okay, so you can have directions also. Okay, you can give your own directions. Directions are not given. You can give directions. So this is the direction graph for the given network. Okay. So here, see, for the circuit shown in the figure below, draw the graph and write down the trisect matrix by considering a 2 ohm resistance branches as tree. So by considering 2 ohm branches as tree, see, you can form tree, right? See, for this graph, what will be the tree? By considering 2 ohm resistor branches, you have formed tree. Okay, this will be tree. It contains all nodes of a graph having no closed path. This is tree. So we can have tree like this. This is tree. This is what tree. What will be co-tree? It is part of oriented graph which is not covered by tree. It's called co-tree. This is what is co-tree. Use the given graph. Okay. See, tree. This is a tree. See, you are asked to consider 2 ohm resistor branches as tree branches. So I formed a tree by considering 2 ohm resistor branches. Okay, so next, what will be co-tree? Co-tree is the part of oriented graph which is not covered by a tree. So this is the part of oriented graph which is not covered by a tree. Okay, so we can have co-tree like this. Okay, so here this is tree and this is co-tree, denoted represented by dotted configuration. Okay, this is what co-tree. Co-tree. This is what tree. Okay. So here you select a tree and co-tree from the diagram graph. We have selected. Determine the number of links. See, number of links. Number of links means what? Number of what is meant by link? It is a branch of co-tree. It is a branch of co-tree. So how many links do you have here? 3 links. Because number of branches of co-tree is equal to 3. Links are represented by dotted lines. Okay, these are all links. These are all links. Okay, so number of trisect currents is equal to number of links, which is equal to 2. Next, you find the number of links. Number of links is equal to 3. Number of links, nothing but number of branches of co-tree, which is equal to number of trisect currents. So you're going to have 3 trisect currents: I1, I2, I3. Okay. So here, the number of trisect currents to be assigned equal to the number of links. So first we have to draw the directed graph for the given network and determine the number of links. Number of links is number of branches of co-tree. Okay, we have determined the number of trisect currents must be equal to the number of links. Number of links. That's why number of trisect currents is equal to number of links is equal to 3. Okay, so you are going to have three link currents. You have 3 trisect currents. Trisect currents are link currents. Okay. I1, I2. Okay. The number of trisect current here. Trisect matrix represents the relation between number of link currents and number of branch currents. Number of link currents. Okay, number of link currents. These are all link currents, trisect current. Number of branches. It represents the relation between number of branch currents or number of branches, number of trisect currents, trisect link current or trisect current. Trisect current, right? Number of branches, number of trisect currents. Right. So that's why here trisect currents here link currents or trisect currents and branch currents or branches. So it represents the relation between number of link currents and branch currents or branches. So you can write. Okay, next. Assign trisect currents. Assign trisect currents such that they flow through only one link in the path. Okay, so a graph consisting of tree as well as co-tree, and you have to assign trisect currents. Okay, so we are having graph like this. Okay. Tree and co-tree. Okay. 4, branch 5, branch 6, branch 2, branch 1, branch. So now assign trisect currents such that they flow through only one link. They flow through only one link. And one more thing is the direction of the trisect current should be same as the direction of link. Okay, so now you assign trisect current. So that should flow in only one link. Assign trisect currents such that they flow through only one link in the path. Okay, so in this path, I1, this is I1. It should flow through only one link in the path, and the direction of trisect current should be same as the direction of link. Okay, both should have same direction. Okay, here see. This is the direction of branch. This is the direction of current. Okay, both should be same direction. Okay, next I2. Next you can have I2 that should flow through only one link. So you can have I2 like this. Okay, branches. Four, four, five, six. Right. Okay, now right. Now assign tensor current. Tensor current should flow through only one link. Okay, we can have tensor current like this, and the direction of tensor current should be same as the direction of link. So here see I1, direction of I1 is same as the direction of link port. Next we can have one more tensor current. The tensor current should flow through only one link. It is going through only one link only. Okay, because in this path one link is present. In this path one link is present. In this path also, in this path one link is present. In this path one link is present. In this path also one link is present. Okay, now let me have tensor current 3. I3. I3 should flow through only one link and it follow the direction of link. So both should have same direction, tensor current and direction of link. Now here. See, now I1, I2, I3, 1, 2, 3, 4, 5, right? Okay, so I1, I2, I3, 1, 2, 3, 4, 5, 6. Okay, so here see, in this loop, in this path, branch 2, branch 4, branch 1. These branches are present, right? Okay, so what we do is, see, you assign +1 if the direction of link is same as the direction of tensor current. So 4, coming to branch 4, direction of link 4 is same as the direction of tensor current. So assign +1. Next, coming to branch 2. Branch 2 is oriented in opposite direction to tensor current. So assign -1. So these two are in opposite direction. Okay. branch 1 is not connected in the path, right? So 1, 0, ascend 0, 0 also ascend 0. So sorry, branch 1 is present in this path. Okay, both are having same direction. So ascend plus 1. In this one. Next, coming to this, branch 5 is not present in that path, right? 0, 0. Next, coming to this, I2, this path. Okay. Branch 5 is having same direction of that of I2. I2 and branch 5 is having same direction. So ascend plus 1. So ascend plus 1. Branch 2 and I2 are having same direction. So ascend plus 1. Branch 3, the direction of branch is opposite the direction of I2. So ascend minus 1. This branch is not present, not present in the path, not present in the path. I3. Okay. These two are in same direction. This is following the direction of this, right? So ascend plus 1. Next, direction of 6 is same as the direction of I3. So ascend plus 1. Direction of 1 is not same as the direction of I3. So ascend minus 1. 0, 0, 0. Okay. So like that we can form Dirichlet matrix. Next, formulate Dirichlet matrix for the directed graphs shown below. Okay. So for this, see here. Actually, this is tree and poetry. Okay. So here A, B, E, B, C. Okay, here branches of tree are what? Fixed. Branches of tree. Half an hour. కొంచెం వేరే రూమ్లో తీసుకెళ్ళు. Branches of tree A, comma B, comma C. Fixed. I'm taking these branches as tree branches. Branches of poetry. Branches of poetry is equal to, I'm taking branches B and E are poetry branches or links. Okay. Now you assign Dirichlet currents. Okay. So what will be? You can have one Dirichlet current. This is what I1, and one more Dirichlet current will be like this. This is what I2. Okay. So you can form Dirichlet matrix. Okay. I1 should flow through only one link. I1 is flowing through only one link, that is D. I2 is flowing through only one link, that is link E. I2 is flowing through link E only. Okay, it may contain any number of fields, but should contain only one link. Okay, like this, you can form dissect matrix. You know how to form that. I'll come back to this equations and transfer. Construct the dissect matrix and write the equilibrium equation in standard KL form by considering branches ABC as three branches. ABC has three branches. Means A, B, three branches. Okay. Depending code. Okay. B, E. Right. Okay, now currents I1, I2. Outer loop, inner loop. Okay. So I1 is flowing through only one link. I1 is flowing through only one link. Okay. So I1 is flowing through only one link like this. I1 is flowing through only one link. Okay. A, C, D. Next. I2 is also flowing through only one link. I2. E, C, A, B. Okay, fine. Now you can form dissect matrix. Okay. Dissect currents I1, I2. How many branches we have? 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. Okay. See. Okay. Here branches are A, B, branches are A, B, C, D, E. Okay, I1. Here see. This path is containing branches A, C, D. Okay. I1 is following this direction of A is following the direction of I1. So assign +1. Direction of B is following the direction of I1. So assign +1. Direction of C is not following I1. So assign -1. Okay. 0. And this path is not containing this branches. Assign 0. Coming to I2. Okay. Direction of A is same as the direction of I2. Okay, so assign +1. Direction of B is same as the direction of I2. So assign +1. Direction of B is same as the direction of I2 +1. Assign +1. Direction of C is not same as the direction of I2. So assign -1. You can form matrix like this. Now let this is B. Okay. So we take this B. 1 0 minus 1. We take this B is equal to 1 0 minus 1 minus 1 1 0. Next row 1 1 minus 1 1 1 minus 1 0 1 0 1. Yes. 1 0 minus 1 1 1 0 minus 1 1 0, right? 1 1 1, sorry, 1 1 minus 1 0 1. Okay. Getting same, right? So these two are same. This question is same as this question. Okay. So we take this as B. Okay. Let J JB, okay, JC JD JE or branch currents. Branch currents. Branch currents. Okay. VA, VB, VC, VD, VE or branch voltages. Branch voltages. Branch voltages. Okay then. B into V is equal to 0. Means from this, what is B? 1 0 minus 1 1 0 1 1 minus 1 0 1. What is V? VA, VB, VC, VD, VD, VE. So this is 2 by 1, 2, 3, 4, 5. 2 by 5 matrix. 2 by 5. This is 5 by 1 matrix. This is equal to 0. Okay, from this, you multiply this row and this column. Okay, you multiply this row, first row, and this column. Okay, then what will you get? VA minus VC plus VD is equal to 0. You multiply this column and this row. Sorry, this row and this column. Okay, then what will you get? You will get VA plus VB minus VC plus VE is equal to 0. VA minus VC plus VD is equal to 0. VA plus VB plus VE minus VC is equal to 0. Okay. V into V is equal to 0. Then we will get KVL equations. KVL equations. Okay. Here we are asked to find equilibrium equation in standard KVL form. Okay. So let me find branch current also. Okay. So let me find branch current. How can you find this branch current? Okay. So let us find branch. Sorry. Let us find branch current. We take B transpose link currents, I link is equal to J. Okay, Then what is B transpose? B transpose is equal to 1, 0, minus 1, 1, 0. Next 1, 1, minus 1, 0, 1. What is I link? I link is I1, I2. I1, I2. Which is equal to, what is J? J A, J B, J C, J D, J E. Okay, then I1 plus I2 is equal to JA. You multiply this row in this column, then you'll get JA. Next, JB is equal to 1. Sorry. JB is equal to I2. Next, minus I2, minus I1 minus I2 is equal to JC. Okay. Next, I1 is equal to JD. Next, I2 is equal to JE. Here. I2 is equal to JE. JE is the branch current. I2 is equal to JE. You can figure it out. JB is equal to I2. JB is equal to branch current JB is equal to, okay, you can have like this. Okay. Branch current JA, JB, JC, JD, JE, right? So you can check it out. See, I1 plus I2 is equal to J. I1 is I1. Okay, this is what? This I2. Okay, so here J is equal to, both currents are flowing. I1 as well as I2 is flowing. So I1 plus I2 is equal to JA. So JB is equal to I2 only. I2 is the only current which is going to this branch. Okay, through this branch, only I1 is flowing. So JD is equal to I1 only. See, through this branch, I2 is flowing. Through this branch, IC is equal to I2 as well as I1 is flowing. I1 plus I2 is equal to C. I2 minus I1 minus I2 is equal to C, JC. Otherwise, minus JC is equal to I1 plus I2. You can check it out. So finally, we can form I1 plus I2. Okay, I2 minus I1 minus I2. I1 I2, which is equal to JA, JB, JC, JD, J. You can check it out. You can also check this VA minus VC plus VD, where VA, VB, VC, VD, VE are branch voltage. So VA minus VC plus VD, right? So here VA, VC, VD. You apply KVL around this loop, then VA plus VD minus VC is equal to 0. You'll get this, right? Okay. This can be found by having V transpose I link which is equal to J. Shall I stop or continue? Okay, what do you say, guys? Shall I stop or continue? I think it will take 15 to 20 minutes.
Sir, last topic కదా sir?
Yeah.
కంటిన్యూ చేయండి సార్, అయిపోతుంది కదా.
Yeah. Now, formulate the cut-set matrix for the directed graph shown below. Okay. Here, cut-set matrix. Actually, I should include the procedure to form cut-set matrix. I'll include and send this PPT. Here, the matrix cut-set matrix means the matrix representing the relation between cut-sets and number of branches. Okay, number of branches and cut-sets. So here, see, here I'm taking ABC are fixed. Okay, means we don't have graph like this. ABC fixed. A, B, C. Branches of tree. Okay, branches of tree. Branches of tree are D. Okay, so D, E. Branches of tree. Okay, here see. Same as in case of cut-set matrix. In cut-set matrix, number of cut-sets is equal to number of picks. Okay, how many picks do you have here? 3 picks. Picks means number of brackets of 3. A, B, C are picks of the graph, right? So number of cut-sets is equal to number of picks. So this is equal to 3. So C1, C2, C3 be the cut-sets. Okay, here each cut-set should cover only one pick. Each cut-set, first cut-set formation, select a tree and co-tree from the directed graph. So we have selected. If the network is given, we have to take directed graph. We have to draw directed graph. Then after, we have to select a tree and co-tree from the directed graph. Here we have selected. Okay, here we have selected. Okay, We have selected tree and co-tree for the given graph, right? Okay, then determine the number of twigs. Okay, number of branches of tree. Number of branches of tree is equal to 3. Number of branches of tree is equal to 3, right? Okay, so number of branches of tree is equal to number of cut sets. Number of cut sets. Okay, so number of cut sets will be equal to 3. C1, C2, C3 be cut sets. Okay, anyhow number of cut sets is equal to 3. That's why C1, C2, C3. Okay, so here a cut set may contain any number of links, but should cover only one pig. It should cover only one pig means let me have cut set. Let me draw cut set like this. Okay, cut set 1. It is covering any number of links like this, but it is covering only one pig. It is covering only one pig, and the direction of cut set should be the direction of same as the direction of pig. In case of trisect matrix, the direction of link current should be same as the direction of link. Okay, so here direction of cut set C1 should be same as the direction of pig. Okay, next let me have C2. You can have C2 like this. This will be C2. The direction of C2 should be same as the direction of B. Okay, next you can have C1, C3. You can have C3 like this. The direction of this is the direction of C3. Should be same as the direction of pig. C. Here C is pig. It is covering only one pig. It is covering only one pig. It is covering only one pig. Okay, remaining or links. It is covering only one pig. Okay, it is covering only one pig. Remaining or links. Okay, so here see, cut set C1 is covering pig A, link B, covering B and link E. Okay, it is covering only one. Sorry, only one pig. Only one pig. Only one pig. So it should cover only one pig, and the direction of C1 should be same as the direction of A. The direction of C2 should be same as the direction of B. The direction of C3 should be same as the direction of C. So the direction of C2 is same as the direction of B. The direction of C1 is same as the direction of A. The direction of C3 is same as the direction of C3 is same as the direction of C. Okay, now if direction of branch is following the direction of cut set, then assign +1. Assign +1. Otherwise, assign -1. If cut set is not covering any branch, then assign 0. How many cuts do we have? 3. C1, C2, C3. Branches A, B, C, D, E. Okay, C1 is covering here. C1 is covering A, B, E. Okay, anyhow, direction of A is same as the direction of C1. Direction of okay. Next, coming to this, direction of D is not same as the so yeah, yes. Next, direction of B. C1. Sorry. This is not covering branch B. This is not covering branch C. C1 is covering D and E. Covering D and E. Right? Okay, then branch D. Direction of branch D is actually this is the direction of C1. Branch D, direction of branch D is opposite to the direction of C1. So assign -1. Next E. Opposite in direction. minus 1. See, here. Okay. Coming to C2. Okay, C2 you can have 0, 1, 0, 0, minus 1. Okay, coming to C3, 0, 0, 1, 1, 1. So now I'll explain this. Here see, C1 is covering A, D. A branch of direction of A is following the direction of C1. So assign plus 1 here. Assign plus 1. C1 is not covering B and C. So assign 0. D. Direction of D is opposite direction of C1. So assign minus 1. E. This is the direction of C1. Direction of C1 is opposite to the direction of E. So assign minus 1. Coming to C2. E2 in this direction. Direction of B is same as the direction of C2. So assign plus 1. Plus 1 here. C2 is not covering A, 0. C2 is not covering C. C2 is not covering D. Assign 0. Coming to E. C2 is in this direction. E is opposite to the direction of C2. So assign minus 1. Okay. C3 is not covering A, B. Okay. So C. It is covering C. Okay. This is the direction of C3. Okay. Towards this node. Towards node. Okay. So assign plus 1. 1, 1, 1. So T minus 1. Minus 1. Okay. Likewise, you can form that matrix. Okay. This is same as the previous column. This is same as this column. Okay. So we got Q. We take Q. Q is equal to cassette matrix. Q is equal to 1, 0, 0, minus 1, minus 1. Next, 0, 1, 0, 0, minus 1. Next, 0, 0, 1, 1, 1. Okay. Now let J, JB, JC, JE are branch currents. BA, BB, and so on. B are branch voltages. Branch voltages. Okay, then KCL equation. We are going to get KCL equation. Okay. Q into J is equal to 0. Then what is Q? 1, 0, 0, minus 1, minus 1, 0, 1, 0, 0, minus 1. Okay, 0, 0, 1, 1, 1. Okay. J. Okay. J will be JA, JB, JC, JD, JE, which is equal to 0. Okay, this is 3 by 5 matrix. This is 5 by 1. Then only matrix multiplication is possible, right? Okay. So from this, we are going to get. Okay, we can have matrix multiplication. Product of these two is what? Product of these two is J minus JC minus JE. Next, JB minus JE. Next, JC plus JD plus JE is equal to 0. You multiply this row and this column. Okay, then you are going to get 1 into J plus 0 into JB, 0 into JC minus 1 into JD. Okay, sorry, so this is JD. J minus JD minus JE. Similarly, JB minus JE. JC plus JD plus JE. Okay, like you can multiply this row and this column. JC, JD, JE. JC plus JD plus JE is equal to 0. Okay, then you can have JA minus JD minus JE is equal to 0. JB minus JE is equal to 0. JC plus JD plus JE is equal to 0. Okay, you can check it out. Yes. JA minus JD plus JE, JB plus JE, JB minus JE is equal to 0. You can check it out in this graph also. See, here JB minus JE is equal to 0, right? JB minus JE. Okay, JB, here branch current JB, here branch current JB. We can apply KCL at this node. JB minus JE is equal to 0. JB minus JE is equal to 0. Okay, like this you can check it out. JA minus otherwise A, B, C, D, E. See, AD, right? AD. Okay. ED. A minus J minus JD minus J. Okay, see, we'll get. So see here, see, J minus JD minus J, right? Which is equal to 0, right? You know, JB minus J is equal to 0. Means J is equal to JB. In place of JD, you put JB minus JE is equal to 0. You check whether it is correct or not. Okay, see, you apply KCL at this node. JA minus JB. Okay, here we can use this again. JB is equal to JE, right? Sorry. If we apply KCL at this node, J minus JD minus J. You're getting this right. So you can get current equation. Okay, next by having Q transpose into E peak voltage, okay, which is equal to branch voltage. Okay, so here what is Q transpose? Q transpose is 1 0 0 0 1 0 0 0 1 minus 1 0 1 minus 1 minus 1 1. What are peak voltage? E1, E2, E3. Okay, this is equal to branch voltage VA, VB, VC, VD, VE, right? Okay, peak voltage are what are peaks? Peaks are ABC, means EA, EB, EC. Voltage, right? So in case of E1, E2, E3, we can write E1 is equal to EA, E2 is equal to EB, E3 is equal to EC. Okay. Then you will get, from this you will get E1, E2, E3 minus E1 plus E3 minus E1 minus E2 plus E3. Okay, which is equal to VA, VB, VC, VD, V. Okay, then here see, VA is equal to E1, VB is equal to E2, VC is equal to E3 only, right? Here VA, VB, VC is equal to E1, E2, E3 respectively. VD is equal to minus E1 plus E3. What is minus E1? So VD is equal to, what is minus E1? Minus EA. Minus E1 plus, what is E3? E3 is equal to EC. Okay, you can check it out. VD is equal to minus EA plus EC. Okay, what is VD? Okay, VD is equal to, you apply KVL around this loop. VA plus VD minus VC is equal to 0. So you see, VD is equal to minus EA plus VC, minus VA, VD is equal to minus VA plus VC. It's correct. You can apply KVL around this part. You can apply KVL around this part. Okay, then you'll get this equation. You'll get this equation. Okay. So summary of this class, this lecture. Network topology is the study of properties of the network which are unaffected when switched, twist, or distort the size and shape of the network. Okay, graph of a network describe the relation between the nodes, branches, and their interconnections. Okay, you can, so a tree is said to be connected if there is at least one path between each pair of nodes. Okay. Matrix depends the relation between number of branches and number of nodes. That is called incest matrix. A matrix depends the relation between number of link current and branch current. Direction graph is known as direction matrix. Thank you. Any doubts? Any doubts?